Welcome to this presentation of our work, Local Edge Dynamics and Opinion Polarization. My name is Adam Lekowitz. I'm a PhD student at the University of Massachusetts Amherst, and today I'm presenting joint work with Nikita Bala and Cameron Musko. So I'll jump right in and talk about the motivation behind this work. In recent years, scholars have been concerned about increasing opinion polarization, particularly at this intersection between opinions and online social media platforms, which enable information sharing on an unprecedented scale. From our perspective, it seems that the research on this topic has roughly converged to attribute rising opinion polarization to this combination of human dynamics and new dynamics observed online. As an example, one dynamic at play is confirmation bias, which is the human tendency to avoid information that challenges our views and instead seek information that confirms our views. From the social media side, we have platforms that use sophisticated recommender systems to show users content that they'll likely care about and engage with. Dynamics unfold. Specifically, if we view a social network as a graph, we want to understand how local edge updates, so the addition or deletion of connections between users, affects opinion polarization. We introduce a simple model which captures the structure of a social network as a graph and opinion dynamics for each person in that network. We base our opinion model off the well-established Friedkin-Johnson model. Roughly speaking, we want to capture the effects of confirmation bias and a basic recommender system as a simple set of edge deletion and addition rules. With all of this in mind, we also want this model to be tractable, both computationally for efficient simulation and mathematically, so that we can build a deep understanding of the dynamics at play. As stated before, our model represents a social network as a graph, and we consider the undirected variety. In our experiments, we initialize the graph as either a generated network based on a well-known distribution, such as Erdős-Renyi or Berbasi-Albert, or based on the structure of a real-world social network dataset. In the Friedkin-Johnson model, each person, or node, has two metrics of opinion. They have an innate opinion, which is fixed, and an expressed opinion, which is updated over time based on connections to other people. Each of these values is strictly on the interval -1 to 1. To compute the expressed opinion, we essentially take the node's innate opinion as one component plus an average over the neighboring expressed opinions. Once we've computed our expressed opinions for all nodes in a given time step, we can compute polarization and disagreement in the graph. Polarization is roughly defined as the variance of all expressed opinions in the graph, and disagreement looks at each connection in the network and measures the opinion difference across that edge, so the opinion of node U versus node V. So in this model, our edge dynamics change the structure of the graph over time, which then causes the opinions to change over time. And I'm going to start here by presenting a toy example of our edge dynamics model before formalizing everything in subsequent slides. So suppose we have the following very simple graph. Nodes, or people, are represented by the circles in this figure, and edges, or connections, are represented by the straight black lines connecting some nodes. And then the color of each node represents its opinion on this spectrum from red on one side to blue on the other side. So suppose that we consider the node right in the middle of the figure. The question we ask is, how can we rewire this network to simulate confirmation bias and recommendations? The first idea in our edge dynamics is to stochastically delete disagreeable edges. So any connection where the opinions are very different on either side, that connection is more likely to be deleted. But we can't just delete edges, since we want the total number of edges in the graph to stay roughly constant. So we also suggest a new edge which connects the current node to a friend of a friend. This friend of a friend approach is meant to emulate a very simple recommender system, for example, a who to follow feature on a social media platform. Okay, so we've defined two simple rules for edge deletion and addition. Now the network's connections have changed, so we have to recompute the opinions for all nodes in the network. Let's go ahead and do that. After we recompute the opinions, you can see that the opinion of our node in the middle has changed. Additionally, the opinions of the nodes which are proximate to the edge deletion and addition sites have also changed. Let's see one more round of this before formalizing everything. So consider the same node again. We note that our friend-of-friend recommendations do not consider how close the opinions are on either side of the suggested edge. So it might be the case that this new edge we just added actually isn't very agreeable. Let's suppose that the edge dynamics pick this edge to be deleted. Again, we recommend a friend-of-a-friend edge where there currently is no connection. And as before, we must recompute the expressed opinions to reflect the new structure of the network. After recomputing the expressed opinions, we can see that the opinion of the node in the middle has shifted even further towards blue, reflecting the impact of its new neighbors. So the high-level idea for our model is that we alternate between edge dynamics and opinion dynamics many times for many nodes throughout the network until the network reaches some equilibrium. And formally, our confirmation bias approximation is to stochastically remove edges based on their measured disagreement. If a connection is more disagreeable, it's more likely to be removed. Each time you remove an edge, we add a friend-of-friend edge, which currently doesn't exist in the network, and this represents a simple recommendation system. Finally, one component that I didn't touch on in the toy example is the following. In our model, we can also set a percentage of the total edges in the network to be fixed. These edges are never even considered for deletion, even if they are in actuality disagreeable. The high-level idea behind this constraint is that from a sociological perspective, many real-world connections are strong despite differences in opinion. For example, connections to family or coworkers. And of course, opinion and edge dynamics repeat until we reach this equilibrium in the network. So with these preliminaries defined, I'm going to briefly highlight 3 of our main findings from our work. The first finding is that surprisingly, both of these components of our edge dynamics need to be present for polarization to rise significantly. If either dynamic is replaced with a random control, so in other words, if we randomly delete edges or randomly add new ones, we observe that polarization stagnates. It doesn't rise quickly. The figure on the right-hand side is directly from our paper, and it shows 2 main experiments that I'll highlight. The blue lines represent experiments initialized with an Erdős-Renyi graph, and the green lines represent experiments initialized with a real-world social network dataset. So note that when both dynamics are present, which are these solid lines, polarization, which is the y-axis, rises quickly and reaches this steady state. In the dashed lines, we show results for if we have just confirmation bias, edge deletion, and then we add back random edges. And we see that polarization rises very slowly in this setting. And then finally, in the dotted lines, very close to the x-axis, we show results for just friend-to-friend recommendations, and these results are barely even visible, so polarization remains essentially constant if we're just deleting random edges. So at a high level, in our model, we're finding that we need both the human dynamic, which is the confirmation bias, edge deletion, and the platform dynamic, which are the recommendations, to observe these large increases in polarization. Our next main finding is that this model we've defined, including the edge dynamics, is tractable for theoretical work. First, we show formally that the edge dynamics we've defined drive a monotonic increase in the polarization plus disagreement index, which is well correlated with polarization, as long as there are edges in the graph which are sufficiently disagreeable. These are lemma 7 and corollary 8 in our paper. We also provide a mathematical understanding of our model purely based on connection densities. If we split the graph into groups of nodes with similar opinions, we can define an in-group connection density and an out-group connection density. So the in-group connection density captures how likely it is that 2 nodes are connected if they have similar opinions, and the out-group density captures how likely it is that 2 nodes are connected if they have dissimilar opinions. And in the paper in definition 9 and fact 10, we showed that the rise in polarization over time that we observe in our experiments can be comprehensively understood as a function of the outgroup connection density. Specifically, polarization rises as the outgroup density erodes, meaning there are fewer connections between nodes which have different opinions in the network. And then for our final main finding, we uncover evidence that this simple model has powerful effects on the structure of a graph. At equilibrium, our model creates graphs which quote-unquote look like a social network. Particularly interesting is that this finding extends even when we initialize the graph as an Erdős-Renyi graph, which is uniformly random. Running our model causes shifts in the graph metrics, which more closely resemble the metrics of a real social network dataset. We highlight one result which is particularly interesting. There's a lot of literature on the fact that real-world social networks, and in fact human networks in general, often exhibit a power law degree distribution. This means that there are many nodes with small degree and relatively few nodes with very high degree. So here we are plotting the degree distribution for a graph before and after our opinion and edge dynamics model. On the left, we see a typical degree distribution characteristic of an Erdős-Renyi. It's relatively normal. And then on the right, we see the degree distribution of the same graph after we've simulated our model to an equilibrium. We can see that the degree distribution has shifted to more closely resemble a power law distribution. In our paper, we also show a representative degree distribution for a social network dataset, which further supports this result. So now that we've talked about the main findings, I'll briefly conclude with the contributions of our work and several open questions. We propose this simple model of opinion and edge dynamics based on the existing Friedkin-Johnson opinion model. Within this model, we find that we need both elements of edge dynamics, the confirmation bias and the friend-to-friend recommendations, to see a meaningful impact on polarization. And our model is mathematically tractable. So we show theoretical results which largely explain the dynamics observed in our experiments. And finally, we show evidence that our model tends to create networks which have realistic social network-like features. Our findings do also leave several open questions. From a theoretical perspective, it would be interesting to more comprehensively explain some aspects of our model, such as the mechanisms behind degree distribution shift. Our model works with the established Friedkin-Johnson model, but there are also several other opinion dynamics models in the literature which might be more realistic. A question is whether our findings generalize to these. Finally, it would be very interesting to further investigate the model's realism. One component that could facilitate such analysis would be a time-evolving real-world data set with opinion data and connection data. And with that, thank you for listening to our presentation. Our code is available on GitHub at this link, and my email is listed right above that. Finally, I want to give special thanks to ACM SIG-IR for funding the student travel grant, which allowed me to come here in person and present to you all today. Thank you.